I'm sorry, I said that the last video was the last video for Tuesday of week 2. I forgot that there are 4 videos for this one, and there are 4 videos for the second day of this week as well. All right, so we're going to talk about action potentials, and here is our learning topic and outcomes. Okay, it's all related to an action potential. Okay, so an action potential, we're just talking about a big sudden change in membrane potential. Okay, so there's 3 phases. We've got depolarization, repolarization, and hyperpolarization. Now remember from our last video, resting membrane potential in a neuron is -70. We talked about that. Okay, and so if there's no stimulus, no change, that's kind of where we're at. Okay, it's an equilibrium point based on sodium influx, or sodium going in through the sodium leak channel, potassium efflux, so potassium leaving the cell through the potassium leak channels, the sodium-potassium pump makes it more negative, as well as the proteins. They're stuck inside, they're negatively charged, that's what it is. Okay, but even though this is an equilibrium point, sodium and potassium are constantly moving in and out through the leak channels, but then they're constantly being brought back in or pumped back out through the pump. Okay, so there's lots of stuff going on, but this is kind of the equilibrium point based on the number of pumps, the number of channels, the concentration gradient, that sort of thing. Okay, now when it comes to an action potential, there's 3 gates that you need to worry about. Okay, 2 of them are sodium gates. Okay, the sodium channel, this voltage-gated sodium channel, it's a double door. So think about any building on campus. In order to get into it, you have to go through 2 doors. Right? So if only one of them's open, you can't really get inside. Okay? If they're both open, then you can get inside or outside. So we've got a sodium, what we call an activation gate. Okay? At rest, during that -70, that gate is closed. We have an inactivation gate that's open at resting potential, but it doesn't matter because sodium can't move because only one of those 2 doors is open. Then we've just got a potassium gate that is closed. Okay, and so what's going to happen is these gates are going to open and close throughout the phases of an action potential that's going to allow certain ions to go in or certain ions to go out. And those certain ions are sodium and potassium. Okay, but based on this situation, we're at -70. So in order for anything to happen, we have to reach threshold. Okay, and threshold is just kind of the point where the magic starts to happen. Okay, these are voltage-gated channels, those sodium inactivation, sodium activation, and the potassium gates. Okay, for some of them, things change when we get to -55. Okay, so when we hit -55, we start depolarization. D means less, polarization means negative, so we're becoming less negative. When we hit threshold, 2 things happen. The sodium activation gates open, and they open quickly, like immediately. The potassium channels, on the other hand, open, but they open relatively slowly. Okay? And so as a result, almost immediately, sodium is able to go through those double doors into the cell, and that's going to make membrane potential less negative. This is a positive feedback loop. We've had a stimulus, and now the response causes us to get further away from where we're normally at. Okay? Depolarization is due to sodium. Okay? This is sodium efflux. I'm not going to write that because it's just not going to work. Now, to be clear, there is some potassium leaving the cell through this voltage-gated channel, but it's happening relatively slowly because the door is not all the way open. Now, when we go from depolarization, we hit +30. That signals the end of depolarization. We go to repolarization. And the reason that happens is that these sodium inactivation gates close at +30. Okay, we're inactivating depolarization. So as a result, sodium influx stops. Okay, and I'm only talking about influx through these voltage-gated channels. Remember, leak channels are always open, so there's still sodium going in through the leak channels, but that's kind of irrelevant to an action potential. And even though the activation gate's open, because the inactivation gate's closed, sodium can't go in. Okay, once we hit this, the voltage-gated potassium channels are almost all the way open, and so even more potassium is able to go out of the cell. This causes membrane potential to become more negative. Okay, and we call this repolarization because we're returning to our original negative state. Okay, And this is a negative feedback loop, and this is due to potassium efflux, or potassium leaving the cell. Okay, so depolarization is occurring primarily due to sodium influx. Repolarization is occurring due to potassium efflux. Then we get back to resting potential, but we don't stop there. Okay, we end up in this hyperpolarized state, or a more negative state. Okay, and this is because once we get below threshold, those potassium gates begin to close, but they close slowly. They open slowly, they close slowly, so potassium's still able to sneak out. Conversely, the sodium gates, they just reset. So the activation gate closes quickly, the inactivation gate opens quickly, but for the most part, nothing's happening with those gates. So as a result of these potassium gates closing slowly, our membrane potential gets more negative than normal. Okay, it gets all the way down to negative 85. Remember, resting potential is at negative 70. So now we have the second half of hyperpolarization. We have to return back to that negative 70. And this is actually occurring because of potassium influx. Okay, remember those proteins? Those proteins like positively charged ions to hang out with them. Well, so much potassium's left that now there's too much positive charge for potassium, and it can go through all those leak channels. Because there's so many more leak channels, potassium actually comes back in. Okay, the activation gate remains closed, the inactivation's open, and that potassium voltage gated channel remains closed. Okay, so this is potassium influx. Okay, helping us get back to our resting potential. And that is an action potential. So depolarization due to sodium influx, repolarization due to potassium efflux, hyperpolarization for part of it is potassium efflux, and then getting from hyperpolarized to resting potential is due to potassium influx. So what do you need to know? What's threshold? What are the different voltage gated channels, and what's going on with each of these channels during all phases of an action potential?